All right, welcome back. We're now in week 11. How much of the class left to go? About 1/3? No, almost a little under 1/2. Oh my God, it feels like we've been doing this forever. If I'm tired of it, I can't imagine how you must feel. Yeah, cannot see? Okay, hold on. Okay, all right, let's get going. Week 11. We are on linear regression, okay? So, hold on, I'm just going to wait a second for my TA to tell me we're live. Okay, we're good. All right, so let's do this. Last week we took a little look at correlation, and we looked at it in a perhaps interesting and unusual way. We didn't just start with the formula for correlation, because many of you have already seen the formula for correlation. Instead, we started by looking at geometric similarity, looking at how to use cosine similarity to look at the similarity or difference of vectors, right? And then what we saw was that correlation turned out to be a kind of cosine, okay? And you got a chance to play with it on your homework assignments as well. So let's kind of review a little bit what we have done, okay? So for the homework assignment, I gave you the full data sets of that Picolage sticker bundles and accounts business, all right? And I also gave you some hints for things that might make it a little bit faster, but I'll give some more today if I can, all right? So to begin with, let me see if I can go find my assignment from last, okay, let's see if I can find this assignment. 1 second. All right, I think we're there. Okay, Picolage Reco. All right. So let's start by loading the data, okay? So thus far in our class, we have used probably functions like this one, read.csv, to load CSV data, right? Makes sense. However, as the data gets bigger and bigger, you'll find that a lot of the functions that you're used to are a little bit suboptimal in terms of their performance, all right? And let me just try to give one example of it. So I'm going to read this CSV file. This is the read CSV command, okay? So nothing new. However, what I'm going to do is I'm going to wrap this whole read CSV command in a system.time, using system.time. Do you remember many weeks ago, some months ago, a lifetime ago, towards the beginning of the class, I showed you that if you use this the system.time function, it will tell you how long something takes to execute, okay? So I'm going to run read.csv, but I'm going to run it within a system.time command. And that should tell me how long it takes to read the CSV. So let's give this a shot. Let me make this a little bit bigger, so this is what we're doing. And reading this CSV takes about, not too long, 1.8 seconds. That's not too bad. However, for the homework, I also told you there is some packages that make things a little bit faster, and one of them is called data table, all right? And data table gives you an alternative to data frames, which is what you're maybe used to already this semester, all right? And let me just load this table, okay? And let me then run system.time. This time I'm going to use the fread function that comes from the data table package. You may have to install the data table package the first time you want to use it, you know. All right, okay. So let's do a system.time and see how long it takes to read this. Wow. Earlier it was about 1.8 seconds. This is about 0.1 second. It's more than 10 times faster when it comes to reading stuff off the disk, all right? So for those of you who might be doing projects where you're working with millions of records or something like this, you might want to make data table your friend, all right? Now, if data table is so fast, why doesn't R just use data table all the time? Why are we using data frames? One of the things that makes data table so fast is that not only to load data, but also to process the data table is quite fast, all right? Faster than using data frames. And one of the reasons for that is because data table, unlike data frame, allows itself to mutate the data. So let me just go back a little bit towards the beginning of the class where I mentioned when you're usually using objects in Ruby, like a data frame, if you change the object, like you add a column to your data frame, or you change one value in your data frame, R makes a whole new copy of the data frame. It doesn't edit the old copy, it makes a brand new copy, all right? And it does that for several reasons. One is changing data is sometimes considered a bad thing to do, especially if you have multiple processes accessing the same data at the same time. It may be dangerous if one process is changing the data and the other is in the middle of some analysis. It can cause a conflict. So R, by default, says that if you're going to change the data, I'm going to make a brand new copy for you, in case somebody else is looking at the same data at the same time, all right, in memory. So what data table does to become a lot faster is it doesn't make a copy. If you change the data table, it changes the data table. It does not make a copy of it, okay? And for that reason, data table is a lot faster. It doesn't have to keep making copies of itself every time you're editing things or doing things, all right? The downside is that it is possible to have some kind of conflict, maybe not with the kind of analytics we're doing this semester, but if you're doing some analytics that requires multiple processes running in parallel, accessing the same data, this could be problematic. All right? But anyway, get to know your tools. Data table is just one more tool that you have to that is quite a bit faster. All right. So with this fread function, I can also just read this CSV file. So let me do that. Oh, excuse me. Oh, sorry. All right. So now I'm going to read those bundles into a data table. So I'm just using DT to remind myself this is a data table actually. All right. Halim, everything okay? Okay. All right. And then there's one column of the data set that I don't really need, the very first column, if I remember correctly. So it's going to be a little bit messy, but I believe the first column is an account ID, and I don't really need it for my analysis, okay? So what I'm going to do is the matrix is going to be everything except that first column. All right, great. And then I can go ahead and do things like compute cosines and things on this matrix, all right? So before I move, let's see. Okay, so before I move on, so this is just what I wanted to say about data table versus data frame. So data frame is the base R library for loading data, and data table is a high performance package for data processing, all right? Substantially faster, all right, okay. All right, let's move on. So we can calculate things like cosines like we did last time, okay? So we can use the LSA library. That's one of the many libraries in R which will have functions built in for performing cosines and things like that. All right? Now, what happened when you ran a cosine on, okay, so first of all, what is the size of this data set, this matrix? What is the size of this? Anybody remember? How do I find out the size of this thing? How many columns, how many rows? Anybody? Any suggestions? N row and N col. Okay, so I can do N row, and I can say this AC bundles matrix. Bang. So we have, oh, not 10,000. I was completely wrong. So almost 25,000 different accounts whose data we can see here. Okay. And then there's N call that tells me there's 165 sticker bundles that we're analyzing. All right, quite a bit more than last week in class where we looked at just like 3 rows and and maybe 2 or 3 columns. All right, so this is a lot more data. There is one more function called dim, which just tells you the dimensions of this data. So it gives you N row and N call together. All right, cool. All right, moving on. So before I get into how I solved this problem, I want to make one more comment about performance of the code, okay? And that is, in class last week, we used this cosine function that came from the LSA package, right? Anybody have trouble running it on your computer? It ran, okay. Was it slow or was it fast? Slow. All right. Several years ago, when I first started using this data set, I was doing some project with this company, and they were generous enough to let me use this data set for teaching. There were students in the class who said, it doesn't run on my computer. So, but it appears over the years, at least it runs on everyone's computer, all right? So let me do a system.time on it to see how long it takes to run this, okay? Let's go out, make some tea, take a break, stretch out, take a nap, and it's still going, all right? So it takes a lot of time to one by one multiply like vectors against each other. There's a ton of combinations here that we have to do. So it takes quite a bit of time. It took about 21 seconds to do this, okay? And actually that can be a little strange, because if I look at the data, and let me try to do, so let me go back to this little head command that I ran, okay? And if I look at this data, is there anything here that I could take advantage of to make this a little bit faster? As you eyeball this data, and I hope you all take a chance to eyeball the data before you like do analytics on it, okay? Because analytics doesn't do something smarter than you, it just does something faster than you, all right? So if you eyeball the data, you can often see things that your analytics will tell you anyway, all right? What is the most common number in this data set? 0. This data set is full of zeros. And remember, when we're doing cosine operations, we'll be multiplying numbers, you know, from one column against another. If we're multiplying numbers by 0, what's the answer going to be? 0. So whenever we have a 0, we really don't need to do any multiplication. We know the answer right away. We don't have to go through the process. In fact, most of the multiplication that's going on to perform this, to produce this cosine matrix, is wholly unnecessary. The cosine function, if it was smarter, would just say, I don't need to compute like 90% of this stuff. It's going to be 0 anyway. Let me just compute the stuff that looks important. All right? And the cosine function from this library doesn't do that. Presumably, and I don't know why, but I'm guessing presumably because maybe the people using this library, LSA, which I think is used maybe in natural language processing or somewhere. Maybe, maybe not. They're not really dealing with so many zeros in their data sets. All right? By the way, when you have a lot of zeros in your data set, or NAs, like a lot of missing data or just 0 values, we often just call this data set a sparse data set. All right? And sparse here means that, well, hold on. I have to take a vote. What does sparse mean? Before I embarrass myself. Any thoughts? In English, what does sparse mean? What's that? Loose? I want a tighter definition than loose. Any other thoughts? Sparse. What's the opposite of sparse in English? Anybody? Dense. Yes, dense. So what does sparse mean?
Scattered.
Don't say not dense, okay? Scattered. Okay, but yeah, there is data scattered in here, and what does that imply about the data? It's largely empty. It's largely empty. Okay, so sparse means this data is largely empty. There's very few actual values in here. All right. I don't ever hear of data as being described as dense, but because that's the default way of thinking of data. All right, but when we say it's a sparse data set, we just mean that it's largely zeros or NAs. It's largely nothing to compute in here. All right, and there are packages out there that take advantage of sparse data sets by just doing the simple heuristic that I described to you. If I'm multiplying a vector by 0, I don't need to multiply it by 0. I know the answer will be a whole bunch of zeros. I can just put that into the result right away. So I found a package, and I don't really use it much, but I found a package that handles this, and it's called QLC matrix. All right. And so I've loaded that. So just again, how long did it take for me to run this cosine? Does anybody remember? 21 seconds. Wow. Somebody does nothing misses him. Okay. Let's try this. This time I'm going to use the cosine sparse function from the QLC matrix package. All right. We got to be 21 seconds. Do you have your stopwatch ready? Okay. 21. Oh. Wow. That was 0.08 seconds. That's how little data there is in this matrix. All right. There's absolutely no reason to sit down and multiply it all one by one on a computer. All right. So the QLC matrix package gives us this nice sparse cosine function, which allows us to do very fast performance computing on very empty data sets. All right. So fantastic. So that's the package I'm going to be using. Otherwise, this class will take twice as long. Right? I should have told you this for your homework, right? Next time. All right. All right. No, I want you to feel the pain a little bit. I want you to feel the pain so you appreciate it. If I just show this to you, you'll be like, yeah, one more thing professor told us to use. But if you've run this like 10, 20 times for your homework, now you really appreciate it because you lost a few valuable minutes of your life waiting for this. Okay. All right. Okay, jokes aside, how are we going to solve this problem? Okay, so we've talked about sparse data as well, and we've seen that there are things out there that are even faster. Okay, all right, so what do we do with this data set? How are we going to process it, and what are we going to do? Okay, now I apologize. I know for the homework assignment, I accidentally not accidentally, well, I inadvertently said, please go find recommendations in your if you can download the app and run it, go find recommendations. And I realized later that the Android version doesn't have recommendations and the iOS version does. Likely because there are two separate teams for these two different products. So there's a little bit of inconsistency, okay? But not a big deal. So one thing I want to do is I do, however, before doing some analysis, I do want to run some common sense I want to kind of do this exercise first using common sense before we do it through analytic methods, okay? Because if the results I get don't match my common sense, I have to know why that is. Is something wrong with my common sense, or is something wrong with the analysis? All right, so you should hardly ever conduct any kind of analysis without in your head forming some kind of notion of what the results should be. All right? Because what's going on in your head and what we call common sense is what we more formally call theory. All right? Theory is, when we hear the word theory, it's just what do we commonly think about a phenomenon. All right? So I'd like to compare what I intuitively know versus what the data is going to tell me. So before I go ahead and run some kind of fancy recommendation system algorithm, I want to know what recommendations would I as a human being come up with in this data set if I was asked the same question, given a bundle, recommend me other bundles, okay? And the way I'm going to, I think the example I took was Sweet Mother's Day, because guess what's coming up this week? Mother's Day, all right? So let's pick Sweet Mother's Day, all right, as an example. And I believe the recommendations that for me, maybe this is a long time ago, maybe you have other ones on your, if you're using iOS, you may have other recommendations. These were the ones that kind of recommended to me. Hello Baby, Easter Surprise. When is Easter? It's April. Okay, so it's gone already. But why is it giving me these recommendations? Okay, babies, mothers, makes sense, okay? Easter, Mother's Day, might make sense because no, Billy, you say no relationship?
Well, it depends on the day.
Depends on the day. But it's possible that, some people are planning early, not like you and me, okay? But some people are planning early, And on maybe around Easter, they were buying some bundles to like send out some greetings, and they thought, hey, Mother's Day is coming along. Let me buy another bundle as well. Okay, that could be one reason. Maybe people just saw far ahead. These people are much smarter than me. Okay, and they went ahead and bought Mother's Day stickers as well, and maybe that's why. Or wait, hold on. These are designers. These are designer recommendations. These are human-made recommendations. So maybe the designers, they linked Easter and Mother's Day because if you buy Easter bundles, it'll remind you, hey, you should buy Mother's Day bundles as well. Okay? So maybe that's the relationship between them. Spring, is spring upon us? Well, summer is almost upon us. Okay? But something about gardens, birthday wishes. Okay, interesting. But this is what some human designers picked as potential recommendations. Okay? What would I pick as recommendations? So I have one set of human input onto what recommendations might look like. What if I had to do it? Now, I don't have the knowledge of these designers, far from it. What would be my approach? Here's perhaps my simple approach. Where is it? Where is my simple approach? Hold on a sec. Here. So what I'm going to do is since it's Mother's Day, I'm going to take a guess that other things that, not a guess, but I would recommend other things relating to mothers and potentially also fathers, okay? Presumably if somebody is attentive about Mother's Day, they're going to be attentive about Father's Day, all right? So what I'm going to do is I'm going to define the terms mother, mom, dad, father, baba, mama, okay? And these are my terms, all right? Out of trivial curiosity. So in Chinese, mother and father and mother is baba, mama, which is very curious for me because I'm from India, but I'm from a part of India in the east, Bengal, and the words for father and mother are baba and ma. So when I first came to Taiwan, I was like, yes, I know 2 words. But one little thing, we don't say baba mama, we say ma baba. Ma always comes first, okay? So one little difference. So I'm going to search for these words, okay? Let me first run the code, then I'll show you what I'm doing, all right? So, and I'm going to get the name of all the bundles. So names, so I'm going to get the column names out of this matrix, and that gives me all the calendar names, all the bundle names, all the bundle names, all right? And then I'm going to use this grep command I'm going to run it and then I'll explain what it does. And I'm going to search for these terms, mother, mom, mother, dad, baba, all this stuff, inside the bundle names. And that gives me all the bundles which have any of those words in it. So some of them make sense to Mom with Love. That could be a good one. Mom 2013. They need to update this one. Dad 2013. Best Daddy, Sweet Mother's Day. Okay, that's the one I'm looking for, right? Superhero Dad 2. Wow, so popular they had to make a part 2 of this bundle. Oops, Email is in here. That's probably wrong. Okay. So if you had to ask me what were the recommendations I would give with no special analytics ability, I would probably come up with some of these. Okay, that would be my maybe intuitive way of doing it. Maybe you have your own intuition of how you want to do it. Okay. Quick explanation of how that code works. So when I define these terms, you notice I put a little symbol, this straight line symbol in there. That's the symbol on top of the backslash key, I think, on your keyboard. All right. This is called a pipe symbol. It's called a pipe symbol. All right. And this often is used in computing to mean or, like this or that, or, like 2 things or one thing or the other thing. So what these terms are really saying is mom or mother or dad or father or baba or mama. And when I pass this to this grep function basically does searches. It does searching. All right. It can do very powerful searching, but this is an example of searching. And what I'm doing is I'm giving it the terms I'm searching for, and these terms have the OR operation in them. So it's going to try to find one or the other of these in the bundle names that I listed out. Okay? And I'm telling it, please ignore uppercase or lowercase, which means ignore whether it's capital letters or small letters. The last thing, value equals true, says actually tell me the values that you find. If values is equal to false, it will simply tell me the index of the column that it found, which could be useful for other reasons. But if you say true, it'll just tell you the actual words that match. All right, great. And so that's how I come up with my intuitive guesses of what might be reasonable recommendations. So this is what designers think are good recommendations. This is what I think are potentially good recommendations. All right. We haven't even run any analytics yet, but let's do that now. Okay. So cosine similarity. Let's see how we're going to do it. Okay. So let me give you the overall intuition of what my solution does. It's perhaps different from yours. It's perhaps the same as yours. Okay. So first thing I'm going to do is I'm going to run a cosine similarity on all of this. So I'm going to produce a cosine similarity matrix, something like a correlation matrix, but this is cosine, not correlation, okay? Where it will tell me every column versus all other columns, what is the cosine similarity, okay? And as you can see, here are the values. So that'll be the first step I do, okay? So the first step, the first step can be just to produce a cosine similarity matrix based on, based on the actual data that comes in. All right. Now, one of the problems we all had to encounter was one of the things we did is we want to know what are the best recommendations. So I'm sure one thing you all did was given a particular recommendation, you probably sorted, like let's say given, is Sweet Mother's Day in here? Oops, it's not. But let's say given not sticker light, given St. Valentine, or let's pick another one. These are not good examples. Maroon 5. All right, you probably sorted all the other bundles by their cosine similarity value, right? But then, if you do that, one of the top recommendations will be the same bundle itself. It'll be Maroon 5 again, right? The problem is harder if you have something like this bundle between, because its results between may not be the first recommendation, might be the second or third or fourth recommendation, right? So one of the problems you're going to face is if you take one row of this matrix now to come up with recommendations for that bundle itself will be in the answer set. And how do you remove it? And I think one thing you guys figured out is you can just remove it by the name, right? I kind of came up with a different solution, and that's this. After taking the cosine similarity, I realized that every bundle is recommended to itself along the diagonal, right? So it's these diagonal values I do not want, ultimately. So here's what I did. I started by making all these and one more thing. These diagonals are always the value 1.0, right? But there's other recommendations that are also 1.0 in here for whatever reason, all right? How can I discriminate or distinguish between the self-recommendation and the other recommendations that are perfect as well? And my trick was to start by making the diagonals into 2.0, an impossible cosine number, 2, all right? That way, when I run through this matrix row by row, and I sort each row by the cosine similarity, the value 2 will come to the first column, right? It will always be the top recommendation, and it'll be the first recommendation if I sort them that way. And that way, if I sort them and get the names, then the first column will always be the same as the recommendations, the bundles that I'm comparing with, all right? And then all I have to do is just delete that first column. And now every row is just clean, pure recommendations, not against other bundles. All right? Oh, excuse me. So, so my data looks something like this now. My code looks something like this now. Start by, and by the way, this is all in a function that I called cosine recos. So this is one big function, all right? So this is my function called cosine recommendations. It takes the items matrix, all right? And the first thing it does is it performs the fast sparse cosine operation on it. Second thing it does, it transforms all the diagonals to 2. The third thing it does, and it does 2 things at once, which might be a little confusing, is it sorts. So I'm using the apply function to sort each row by its cosine value. All right? That will bring all the number 2 recommendations to the first column. All right? And I'm not interested in the values of the cosines. I'm only interested in the column names. So I've made a little smaller function called row recommendations. And if I apply this over my matrix, then it will produce for me something like this. All right, it'll produce this matrix right here for me, where the first column will be itself, the row name itself, and the following columns will be the best recommendation, second best, third best, etc. All right, and then I delete the first column, and I simply return the top 5 recommendations. Okay? Great. So this is my solution to this problem. This produces for me instantly a matrix of recommendations for all of these sticker bundles. Okay. Any questions before I move on? So if I can try to find my function, it's right here. All right. So given a items matrix, perform the cosine, change the diagonals, sort all the rows, and only get the names. Delete the first column because it'll be the self-recommendation. Return the first 5 columns of the entire matrix. This gives you recommendations for all 165 bundles. All right? Okay. So that's my function. And if I run this cosine recommendations on the AC bundles matrix, then I can ask it, can you just give me the row of 5 recommendations for Sweet Mother's Day? And these are the recommendations I got. I hope it's similar to the ones you got. I hope. I don't know. Let's see. I'm going to check your homework later. Okay? So some of them make sense, maybe. Best Daddy, sure. Maybe if somebody buys Mother's Day, then maybe they also bought a Father's Day or Best Daddy stickers. Some of these others don't really make sense to me. Okay? Why the 4th of July? Why now? All right? Why Tropical Paradise? All right? But these are the recommendations I'm getting out of it. And I'll try to say 1 or 2 more words about potentially why I'm getting these recommendations later. Okay? However, according to my algorithm, people who are likely to buy Sweet Mother's Day are also likely to buy these ones. All right? So even though it doesn't match my intuition, it may or may not match what other things they are buying. Why is a completely different question that the data cannot answer. All right? Before I tried to ask some why questions, I did the same thing with, so that was my cosine-based recommendations, and I could do the same thing to produce correlation and adjusted cosine recommendations. So my correlation recommendations are going to be similar. However, what I'm going to do is I am now going to take, what was it, column-wise or row-wise means? I believe it was column-wise mean. I'm going to mean center, all right? I'm going to mean center my matrix column-wise. So each column will be mean centered. All right? And then I can just reuse that function I wrote, cosine recos. I can just completely reuse it because correlation is nothing more than just cosine similarity done on a column mean-centered data. All right? So that's that. And then these are the recommendations. Ooh, what's going on? Okay, these are the recommendations that correlation gives me. Almost the same ones, just in a different order. Okay, in fact, exactly the same ones, just in a different order. Adjusted cosine does something similar again, but this time it's doing row. It's mean centering the data row by row rather than column by column. All right, and here's Sweet Mother's Day. This time I'm getting some slightly different ones. All right, interesting. Okay, and just to make sure that we're not completely crazy, here's one last thing I like to do. Rather than using any kind of algorithm, any kind of like actual recommendation algorithm, I just want to make sure, and this is going to sound ridiculous, but I want to make sure this is different than just randomly picking things and recommending them. Okay, so the last thing I did, and I don't know if my the code for that is not in the handouts, but the last thing I did, it will be in this video, however, is that I simply took the bundle names. I took all the bundles that are not Sweet Mother's Day, set a seed, and just picked 5 of them at random. Just to show myself that the recommendations I'm getting are not like completely random, all right? They don't like overlap largely with just the random recommendations. So I'm definitely systematically, whether I use cosine correlation or adjusted cosine, I'm getting very similar recommendations, these ones, all right? And what else? So I'm getting these recommendations, and they're largely similar. Now, for reasons I'm not going to go into exactly right now, is that often in industry, the adjusted cosine is the preferred one, all right? And the correlation, I don't really see it used much for this purpose. Of course, correlation used for a ton of other purposes, but not for like this kind of recommendation system. It's usually cosine or adjusted cosine that people feel works the best for this kind of system, all right? So what is the difference between the cosine, the correlation, and the adjusted cosine? Well, I mentioned that the correlation simply mean centers the columns before performing a cosine, all right? And what that's effectively doing is that it makes each number in our data set relative to the average of that bundle. I mean, if the bundles are columns, it means that each number in the raw data set before we perform the cosine is transformed to being a difference from the average of that column. All right? So we're getting a relative sense of how often a particular bundle is purchased by a particular user relative to the other users. All right, so that's what correlation is doing. And the adjusted cosine, by doing row-wise mean centering, it's kind of telling us any given cell in the matrix becomes relatively how often is a bundle purchased by this account holder relative to the other bundles purchased by this account holder, all right? It's just two different interpretations of the data. Okay, we can also see visually the difference between a cosine and a correlation. So the formula are almost exactly the same. It's just that the vectors are mean-centered column-wise in the correlation, and the cosine they're not. Right? And as you can see here, after mean centering and performing the cosine, our values begin to look like, not performing the cosine, but after mean centering, our values look like this. The vectors themselves, so in a cosine is measuring the angle between these vectors. The correlation, because it uses a cosine, is also measuring angles, but between very different vectors. These are the mean-centered vectors. All right? So essentially, in the correlation, we're stretching the data out in this example so that it kind of occupies 3 quadrants rather than just a single quadrant of our space. And the origin, rather than being in the bottom left, is now somewhere towards the middle of the data. All right? So that's the essential difference between the cosine and the correlation. However, at the heart of both is simply measuring, in a way, a normalized angle between vectors. Normalized because the cosine gives you values between -1 and 1. Okay? So that's what we talked last week about data similarity, the difference between cosine and a correlation. And my intention of showing this to you was to kind of effectively show you that we're going to be talking about correlations a lot this semester, for what's left of the semester. But correlation is just, it can be thought of as in a geometric way as finding, you know, a similarity between vectors using angles. All right? Okay. Moving on. So I also looked at something like this slide last week, but I want to come back to it with what you've done in your assignments. Okay? Let's see. Okay. So in the assignment that you did for your homework, I asked you to produce some figures like these ones, and I'll go into them a little bit more detail a little bit later, but just to start with, I can, oops, actually, I just need this one. All right. Let me get the simulation going. So interactive regression. All right. And essentially what you could do was, you know, produce some, okay, something like this. All right. And that gives you, and when you do that kind of shape, it tells you the correlation and also a regression slope. Okay. And I'll get to those regression slopes and things like that in a moment. All right. Oops, excuse me. All right. And if you store the results of this operation, then you will get all this data kind of fed into your system. All right? You will get the points actually stored. Escape. So now points is the points that I literally clicked on. All right. And we can run a simple correlation on the points. And this gives us a correlation table, and about 0.95 in this case is the correlation of x and y. All right. So statistically speaking, so we looked at this kind of geometric interpretation of correlation. Statistically speaking, what is it doing? So last week I mentioned that one way to think about, statistically the way to think about maybe what a correlation is doing is that it's taking a covariance and it's fully standardizing it. All right, so I would like to just kind of break this down a little bit here. Covariance, what is that again? So in the weeks prior, we've studied variance. So you're all comfortable, hopefully by now, with variance, right? And once again, variance was simply when you take a mean-centered vector, multiply it by itself, sum it up, and divide by degrees of freedom. That numerator is called the variability. So variance is, you can think of it as the average variability. We're just simply dividing by how much data we have, n minus 1, roughly. Okay? So if variability is called sum of squares, variance is sometimes called mean squares. All right? And that's for x. We can do the same thing for y. And covariance is this really interesting adaptation of that, but to two vectors compared to each other. So covariance is like the variance of x and y at the same time. And all we do is we take the mean-centered x multiplied by the mean-centered y. All right? And we sum these up and divide by the degrees of freedom. It's almost exactly like this formula of variance, except it's x and y in the numerator, not just one variable. It's two variables at the same time. All right? And that gives us a covariance. And let me see if I'm going to do this on a following slide. Hold on. I'm just going to jump through where my following slides are. I'll do this once here as well. So I have these points, x and y. I can get the covariance of x and y in a couple of ways in R. One is I can simply ask for the variance of points. All right? And this gives me the variance of x and the variance of y in the diagonal. The off diagonal is the covariance. All right? So the covariance of x and y is 189.65. May not mean a whole lot to us right now. There's another way to get the covariance. There's a covariance function, so we can say points x, points y. All right? And that gives us the covariance of x and y. And the covariance, so if the variance is the dispersion of x or the dispersion of y, covariance is like the joint dispersion. How do these two things disperse together? All right? As x and y, what is the variance of this whole system of x and y? That's what the covariance is essentially telling us. Okay? Now, understandably, the covariance may not be very meaningful to you and me. That number, 189, what is that? I mean, it doesn't make sense. X and y in this case don't even have units, but 189 also really does not make a lot of sense to us. To maybe make it help us make it makes some sense, or to give it some kind of scale, we can normalize it. We can divide it by the standard deviation of points $x, all right, times the standard deviation of points $y. This is effectively standardizing the covariance by dividing by the standard deviation of both the variables involved, x and y. Oh, sorry. All right. And that gives us our correlation. So the correlation is just a fully standardized covariance. All right. And our correlation here is 0.95, just as our figure told us. All right. And as you saw, a figure like this has a high correlation. A figure like this potentially has no correlation. And I'll come to those in a moment. Okay. But statistically, this is one way we can think of what correlation is. We thought of it geometrically. This is the statistical point of view. All right. And there is an interesting kind of dualism where you can think of correlation either geometrically or statistically. It's the same. You arrive at the same formula, basically. Okay. We can again look even further into this kind of two views of correlation. All right, where correlation is the covariance fully standardized. And the way that we can potentially think about it is that if you work out the correlation, there'll be degrees of freedom associated with the covariance, there'll be degrees of freedom associated with the standard deviations, but those degrees of freedom cancel out, and you get a formula that kind of looks like this. Right? That's like the formula for correlation if all the degrees of freedom cancel out. Okay? That numerator is kind of interesting. It's one vector's mean-centered times the other vector mean-centered. All right? And this expression also has a meaning in geometry. All right? So if you take two vectors, A and B, then if you think of, so if you look at these as two different vectors, and imagine that we kind of like draw this so one of the vectors is just straight up, all right? Doesn't matter which one, but let's pick one vector like vector A and make it straight up, and let's pretend there's some light coming in from the left, like some sunlight from the left, and vector B kind of casts a shadow on vector A. Okay, can you see that? So this is the length of vector A. This is the length of vector B, is the length of this vector. And imagine that vector B casts a shadow on vector A if the light comes in perpendicular to vector A. This length here, the length of the shadow, this is what you did in middle school when you learned geometry, okay? This is the length of B times the cosine of the angle between them, all right? And that actually happens to be the numerator of your correlation, if you work it out. So essentially, what correlation is doing, at least in the numerator, is it's asking, does the how much of the length of vector B is lost when we cast a shadow onto the other vector? Okay. If vector B was on the same direction as vector A, then its shadow on vector A should be the length of vector B. But we're losing some of that as vector B begins to disagree with vector A and go off in a different angle. All right? So essentially, correlation is kind of just looking at how does vector B agree with vector A in the numerator, and then in the denominator, it's essentially just standardizing that answer to be between 1 and minus 1. Okay? All right, so that's all I want to say about correlation as you can view it from a statistical point of view as a covariance fully standardized, or from a geometric point of view, which is the agreement between two vectors, once again standardized to 1 and minus 1. All right? So that's our correlation. And then for the actual assignments, I asked you to look at some of these correlations and see, do these actually make sense with different figures that you could possibly draw? Okay? So we drew a correlation where if the points are in a strong diagonal, we get a strong correlation. And I think one of the questions also kind of asked you, if I draw these in a fairly straight line like this, what does the correlation look like? And I think you'll mostly find that the correlation gets very close to 0, right? So this, and why is that? What does that mean? What does it mean for the correlation of x and y to be almost 0? So it tells us here that the value of x, whatever it is unrelated to the value of y. Let's think about it in another way. If I just take one part of this figure at a time, like between, let's say, 0 and 10, okay? As the value of x increases, you'll see that y is sometimes 0, sometimes is above 0, sometimes is below 0, it's again at 0. The value of y doesn't seem to care what the value of x is. The value of y could be 0, above, below, whatever it wants to be. That's what a 0 correlation is. It says the value of y doesn't really care what the value of x is. It's not going to increase as x increases, or decrease as x increases or decreases. All right? So as we go down and x gets bigger and bigger, y just keeps jumping between positive and negative and around 0. It doesn't really care about the value of x. Okay? So that's our 0 correlation. And a negative correlation, unsurprisingly then, is something like this. As x increases, so this is a very strong negative correlation, a near perfect negative correlation. So as the value of x increases, the value of y decreases. That's a negative correlation. Okay? So these three shapes should be very obvious to you: a positive correlation, a negative correlation, and a 0 correlation in 2 dimensions. All right? I asked you, however, if you can make these numbers not make sense, can you produce figures where these numbers do not make sense? All right? And any suggestions? How can I make a figure where the correlation doesn't make sense to what I'm watching? So I think some of you came up with answers like this, which is when you split your data into 2 groups. All right? If my data is in 2 groups, I can do some strange things. For example, here is an obviously strong negative correlation. Okay, it's like a 0.8 negative correlation. However, if this data had another group which was exactly the same, a very strong negative correlation. There's two groups of people now. Okay? You'll now notice that, so there's two groups with negative correlations, but the overall correlation is actually strongly positive. All right? Which means, like, let's say we were doing some experiment, and let's say one group was like women and one group was men. As whatever X is increasing, let's say we're giving them some medicine, and we hope that Y is, their symptoms reduce, okay? So for men and women, as we give them more and more medicine, we would like to see that, the disease symptoms are decreasing. And it works for men. It works really well for women as well. Negative correlations between the amount of medicine I give and their symptoms. However, if I didn't visualize this, it looks like as I give more medicine, people are getting sicker, right? That's what the correlation is actually telling me. It's telling me the opposite of the actual story. So there is a danger in this thing we call correlation. It doesn't always match what's happening in reality. It can be actually the opposite of what's happening in reality. Okay? So in my story here, let's say this is men and this is women. As I give them more medicine, in each group their symptoms decrease. But if I put the two groups together, the correlation is strongly positive, which might lead me, if I didn't visualize this, to making the conclusion that this medicine is making people sicker. It's not, it's actually working. All right? By the way, the blue line here is not the correlation line, this is a regression line. So this is the regression slope here, okay? It seems to be, appears right now to be different than my correlation, but I'll come back to that. Any other figures that can produce funny things? Any thoughts? Funny results? How about a simple parabola, right? Imagine that x-axis is something like how many hours I'm studying for an exam in the 2 days before the exam, all right? So as I study for an exam, my grades should, get better and better. Of course, at a certain point, it should kind of fall off as well, right? So let's say over 2 days, I've studied for 20 hours. That's a lot. It's like I've studied one whole day. That, there is a limit. Beyond, let's say beyond 15 hours, I'm really not getting better. I'm just, staying the same. And if I keep studying instead of sleeping, maybe my performance starts falling. And it's possible at the end, I just forget to show up at the exam. Right? So I'm just telling you a funny story where as I study and study, I get better and better, but beyond a point I'm getting tired and tired, and then I'm like just falling asleep at the exam and my grades are going back down. It's a ridiculous story, but it, kind of matches reality to a certain degree. But here's my point. There is a clear relationship between x and y. It's a parabola, right? It goes up and then comes down. We understand this relationship intuitively. We understand this relationship. But does the correlation understand this relationship? No. It's a zero correlation. It says there's no relationship between x and y. That's completely wrong. All right? So correlation is a linear perspective of relationships. And we'll talk in the coming weeks what we should do when our relationships are not linear. All right? Can correlation still be helpful? Potentially. We'll see that later. All right? So these were some examples that I wanted to give. All right? Oh, and one more. This is my last example of this set. And I wonder, so by the way, how many of you did the two groups thing where one negative, the other negative, or one positive, the other positive, and the correlation is the opposite? How many of you did something like this? 1, 2, okay, about half of you tried that. How many of you did the something like how many of you did something like the parabola where it goes up and comes down? Okay, about a third of you, something like this, right? Okay. I noticed one student in the class posted this on Facebook, right, Gil? And this was my favorite one that he posted. it shows you that your results have nothing to do with your happiness, right? Zero correlation and a smile. Okay. Okay, so I thought that was funny as hell. Okay, one more example and another important example. All right, so I have data that is very strongly correlated. It's nearly a perfect correlation, right? Like a 0.9 correlation is nearly what we would call a perfect correlation. And then I have one more point to put on this plot. And where am I going to put it? Bzzz. Let's put it down here. What's going to happen to this line? Will it become a little less positive? 0? Let's take a look. Just 1 point. How many points do I have already? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's make it 10 for good measure. Okay? And then 1 point out here versus 10, right? Often, especially if you're new to statistics, it feels like 1 point, what damage could it possibly do? Let's do it. 1 point out here. Bang. We have a negative correlation. It just took 1 point to screw this whole thing up. All right? And why is it screwing it up? Why is it screwing it up so much? Like when I was putting these 10 points here, every point didn't make a big difference. Why is this point making such a huge difference? Anybody want to take a guess? What's so special about that point? Luis, can you say that again?
Outlier.
It's an outlier. Okay, great. So why is it affecting my correlation so greatly? Just 1 point. Bias, separated. The distance. Something about the distance. What is it about the distance? Let's go back and take a look at our formula for correlation, right? What you see here is as a point becomes more distant from the other points, essentially its distance from the mean is growing tremendously, right? And what happens as a point in its x and y directions is distant from the mean. That difference is compounded. We are multiplying its distance from the x mean and its distance from the y mean. So in a sense, its distance is kind of like getting squared here, right? Like the further it is, its impact on the correlation is not like linearly bigger, it's quadratically bigger. All right, so one thing about correlation is the further a point is from the mean, it has a much greater leverage, it has a much greater influence on these statistics like correlation. Its difference in each dimension is multiplied by its difference in the other dimensions. If its distance from the average in x and y and potentially other dimensions increases, these differences are multiplied together. It has a multiplicative effect, all right? So an outlier in multiple directions has a massive effect. An outlier in just one direction may not have too big an effect. But if it's bigger on all directions, it's going to have a much bigger effect, okay? So if I was to do this example, and in this case, if I just, here are my points, and last time my point was out here somewhere, right? What if I didn't make it, so let's say the average of x and y is somewhere here. The average point is somewhere here. My point was out here. What if I just made it different in the x direction, but not in the y direction? I'm going to assume the average of y is somewhere around here, okay? If I do this, my correlation changes a lot, but it doesn't become negative, right? It becomes negative as I am different in multiple directions, like it completely flips sign, all right? So we've seen a few interesting examples here. We can have misleading zero correlations, where the correlation is, not detecting a pattern because the pattern is not linear. All right. We've seen the story of outliers, and now if we go back to the beginning of the class, why are people interested in outliers? It's not just because they're different. If they're different in multiple dimensions, they can completely reverse the relationships that I'm thinking of. They can have an oversized effect on my statistics. Okay? Here, both the slope and the correlation have completely flipped to become negative. If I didn't visualize the data, I would have a completely wrong understanding, an opposite understanding of what's happening based on just one point. This is why statisticians are often afraid of outliers. Okay? And then there was this example, and I have a little story written here that you can read later. If I have two groups which have similar relationships, like, negative and negative, it's possible for them to be positioned in such a way that the average of the whole data appears to have a positive correlation. All right. And this paradox has a name. This is Simpsons Paradox, where local subgroups can give you a completely mistaken notion of what the data actually looks like. All right. So one of the reasons I made you do this homework assignment is so that you can visually realize it's not very hard to create data sets whose correlation seems to have nothing to do with its actual pattern. It could, but it may not as well. All right. And think about that when you realize that a lot of, almost all the algorithms we're using in data sciences is somehow based on correlation to some degree. Okay? You may not see it in the data set, in the algorithm, like maybe you're studying a deep learning algorithm or a neural network or something, you're like, I don't see a correlation in there, but there's something in there that is drawn from a correlation. And often that is the dot product of two vectors. You will find that in a lot of different algorithms in machine learning and data science. All right? And essentially, they're doing something very similar to a correlation. So they're vulnerable to all the things we're talking about today. So these problems I'm showing you here, these are not true just of classical statistics. It can also be true of a lot of modern machine learning algorithms. All right? Okay. So anyway, yeah, I do want to show you this interesting problem. And in general, and here's my kind of sorry about this figure, in general, you are lucky if you have subgroups that agree with each other. Like here I have 3 subgroups which are relatively flat. The average relationship is flat. Here I have like 2 subgroups of data, these ovals, and they have positive slopes, so the overall slope is positive. And the same if you have 2 subgroups with negative slopes. But wherever subgroups disagree with one another, you can have strange results. Like 3 subgroups that are all positive, the overall relationship is negative. 3 subgroups which actually have no relationship within themselves, but overall the relationship looks negative. It's not. And the same thing on the other side. In fact, it's much easier to have subgroups that are screwing up your story than helping your story. All right? Any questions about correlation just by itself before we talk about regression issues? Are you okay with this? All right. Now, when I asked you to do this assignment where you kind of visualize the points and you look at the correlations, I also asked you to take a look at this regression line and the regression slope. And I haven't said much about regression because I'll talk about it today, the next week, and potentially the week after. Okay? So what is this regression slope? Actually, before we get into regression, I know it's a little bit early to take a break, but why don't we just take a short break and come back and talk about regression? Okay? Because it's going to be a whole new topic, so I'd like to just refresh our thinking and just like put correlation to rest for a second because we'll come back and we'll talk about regression instead. Okay. So let's just take a quick, let's just take like a 5 to 10 minute break, and we'll come back and talk about regression. Okay. All right. Thank you. You're welcome to go outside and use the restroom or whatever you want to do.